Today I'm going to talk about Probing Neural Network Comprehension of Natural Language Arguments by Timothy and Hengyu. People want to understand neural NLP systems, and one of the methods to do this is by applying tasks that require significant knowledge and examining their performance on these tasks. One of the tasks that this paper is looking at is called Argument Reasoning Comprehension task. Let us first look at an example in this dataset. There are 4 sentences in this data point. A claim that Google is not a harmful monopoly. A reason people can choose not to use Google. The reason supports the claim. There are 2 other sentences, a warrant and an alternative. The warrant supports how the reason supports the claim. So the warrant in this example is other search engines don't redirect to Google. So people can choose not to use Google, so Google is not a harmful monopoly. However, if you use the alternative, all other search engines redirect to Google, then people can actually choose not to use Google, which greatly inhibits the support of the reason towards the claim. To the contrary, the negation of the claim is true. If all other search engines redirect to Google, then people cannot choose not to use it, then Google is a harmful monopoly. Given the claim, reason, warrant, and alternative sentence, we want the models to predict which one of warrant and alternative is the warrant. This is the argument reasoning comprehension task. The authors found that by using BERT, they have surprisingly high test set accuracy, 77%, whereas other participating systems in this task do not exceed 60% of accuracy. This is very, very high improvement against other systems. What is the BERT model that they use to get such a high accuracy? They input a COS token and concatenate the claim, the reason, and the warrant. They use a separation token in between the reason and the warrant. After passing this sentences into BERT model, they take the output vector of the COS token and put them into a linear classifier layer and fine-tune this whole system. Note that the ARCT task is relatively small. There are only slightly more than 1,000 training examples. So it's natural to ask whether the language models overfit or whether they focus on some statistical cues to solve the task instead of understanding the deep semantics. What is a statistical cue? An intuitive example is that if there are some words that occur in only the positive examples instead of the negative examples, then regardless of what the word means, whenever I see this word, I give a positive classification. Then this is an example of using the statistical cues instead of understanding the deep semantics for classification. In this paper, the authors focus on unigram and bigrams for statistical cues. And in order to measure the effectiveness of the statistical cues or the impacts of these cues into these models, they used applicability, productivity, and coverage to depict. The applicability is the number of data points where it occurs with one label but not the other. So in order for a data point or a cue, unigram or bigram, to be applicable, it occurs with one label but not occurring in the other. The productivity of a cue is defined as the proportion of the applicable data points for which it predicts the correct answer. So among those applicable points, applicable cues, some of them correspond to the correct answer, some of them correspond to the incorrect one. And the productivity computes the proportion of the applicable points that correspond to the correct answer. So naturally, in order to let the productivity be meaningful, it has to be larger than the natural constituency of this label. Let's say if there's a binary classification, the m is equal to 2, then a meaningful pi k has to be larger than half. So if pi k is larger than half here, we know that there are a lot of statistical cues, unigram or bigram here, that are applicable, that are predictive to the final correct classification. And finally, the authors define the coverage as the proportion of the applicable cases over the total number of data points. Applicability divided by n. The authors found that the strongest statistical cues include those that are not very semantically rich ones. Let's say not, is, do, and are, and will not, cannot. Let's say if I were doing the classification task, the AICT task, I will actually look at those nouns and verbs instead of first looking at this not, is, do, are, the stop words. However, the language models look at these statistical cues and prove that, and they show that these cues are able to give them high performances. In addition, the authors used probing experiments to show how much that the BERT models are relying on these statistical cues. They use several sets of experiments. The first one is given your claim, your reason, your two candidates of warrant. You predict which one is the candidate, is the correct warrant. The BERT is able to give 77% at the best attempt. They did some deconstruction. First one, they removed the claim and just use R, W, and A to give a classification. This is called RW set. The second one is removing the claim and just use the remaining 3 sentences. This is called the CW set, and also they remove both. This is the W experiment. They found that surprisingly, the W experiment has 71% accuracy. This is only 6% lower than the best performance. What does this mean? This means that by only looking at the candidates themselves, the model is able to get 71% of accuracy, which means the really semantic and logical parts of this model can only contribute to at most 6% of the performance improvement. And the other two experiments get somewhere between 71 and 77%. This is 73.2 the max and 75% max for R and W. In addition to these tests, the authors also used adversarial test set. The adversarial test set can be conveniently constructed from the setting of the ARCT dataset. They used an original and an adversarial setting. The original setting uses the reason and warrant to predict the claim, and the adversarial one uses the incorrect answer candidate to predict the negation of the claim. If the model understands the semantics, then they should perform well on one scenario after pre-training from the other scenario, because these two scenarios are basically measuring the same thing. Let's go back to this the example that I mentioned above. The original setting is that people can choose not to use Google, and other search engines don't redirect to Google to infer Google is not a harmful monopoly. And the adversarial setting is that all other search engines redirect to Google, and people can choose not to use Google to predict that Google is indeed a harmful monopoly. These two settings are actually equivalent, but surprisingly, the models perform very, very poor between transfer tests. Actually, all results were worse than random due to overfitting the queues in the original training set. The moral of the story? With little or no understanding about the reality underlying these arguments, good performance shouldn't be feasible. About other contents of this paper. The investigations confirmed that BERT is indeed a very strong learner. It can choose between which statistical cues to rely on, but they do rely a lot on the statistical cues, and they fail to have deep understanding for many of the semantic tasks. In the future, more robust evaluation instead of only the accuracy is expected to understand the capacities of these neural models.